be shorter, I guess, because there are just three exercises, but I mean, you know that you can ask as much as you want. Okay?
I don't think
So, okay, so we have a lot of questions, that's nice. So, maybe, Mariam, you can start. If you have some, like, specific question, if you got any big problem, then maybe we can stay a bit longer after we finish, so we check together. So, did you manage, for instance, to check, like, to create a two tunnel or not? Wait. Wait a second.
But I cannot go to the.
Okay, so
Yeah.
you,
Can you hear me?
yeah, now yes, yeah. So you cannot have tunnel, like you cannot enter tecla home mountain and locally, okay.
No, I cannot go to the P4 VASP.
Running the two systems. Uh,
Exactly.
do you have,
I'm sure that I'm doing something wrong, but I don't know what's wrong with it. So I think maybe the comments are there, not the problem.
Microsoft with you? I mean, are you with your personal computer now?
Yes.
I mean, if you have time, we can try now, you know, together. Like if you can open the virtual machine, you know, and share the screen, then we just do it now.
I need to change my connection and this kind of things.
Like, so take your time. I enable the sharing for you. In the meanwhile, while you get ready, maybe we can start with one question from here so you don't feel
Yeah, sure.
So, a question about the exercise.
Yeah, here in the page 8, here they said that replace the ice-spin 2 and the magma 1 by the other hotel. Long, like, LON.
Yeah. Yeah, now I just take the slide so that everyone sees it.
Si quieres pasar directamente de mi teclado a...
No, I mean, like, but I want to take the slide that you're mentioning because, you know, then the people see what is the point. Okay. So don't worry, I'm not opening it right now. So we are saying course for okay, then I share. So you say slide 8 of the answer, right?
Yeah.
So we need to be this one. No, this one.
No. 8. We are in 3.
Yeah, but 8 then is not 8.
Oh yeah, I mean the exercise.
Yeah, but let me, I mean, there is a page. Page. But then, you mean this one?
Yeah, this one.
Okay.
This is exercise, but this is...
Yeah, okay, now I understand. Wait a second, then I open the full answer. So, we are talking about the answer. So, which slide are this one? Page 8 I understood, but like... Okay. So, page 8, but answer 4?
Yeah, but this is... no problem, because, how to say, the first thing I don't understand what this tag means. So I look it for in the wiki about that and understand a little about that, and so I just do what they told in this page, that replace the ice beam and the magma by this two tags, and the program did not run.
I see.
Also, I look for the wiki, and from their documentation that I need to first do another optimization by just do this without size ice-spin equal to 2, and just without magnetization, without taking account magnetization. So I do that and pass the chart, chart card and wave card to the new a new calculation, and I also do that I charge equal to 2, I think, one or one or one, I think.
Okay.
And
So we are talking about this exercise, right? That you did, right?
yeah, that's the new.
Yeah, this
Oh,
is
wow.
yours. So now you are talking that you change this and you put like L non-collinear equal to true.
I charge and yeah, I start equal to read the wave card and the chart card that come from calculation previous calculation without taking count magnetism.
Yeah.
And it don't work.
I understand. So I don't know if you remember what I said yesterday, but like that this L non-collinear, like you cannot run it because we don't have the VASP compiler that can run it. So it's like there is no way you can make it run. The only way that you can make it run, we should ask the IT manager, so Martin, to change a line in the make file of VASP. So that's the reason why I removed the other exercises in the in the folder, and that's why the 3 folders that I gave you were without this L non-collinear, because there is no way you can run it.
Okay.
And also, like as I said yesterday, I would not spend time with that, because the time that we spend with this L collinear, I would not say that is wasted, but almost, because it will never work with that. Okay, so that is my answer.
Okay, interesting.
So, but the point is, just to clarify, is not your problem, it's the problem of VASP. Internally, the version of VASP that we have.
Okay.
So there is no way that you can make it run.
Sorry.
Here. No, I mean, not sorry. I mean, it's not your fault. I'm just sorry that you ran, like you tried several times to make it run, but there was no way you could make it run. Okay? So.
Okay. And the other one is in I don't know how to do yeah, how to present this figure.
What do you mean? To see?
See, I mean the band D of nickel.
Yeah.
I don't know how to do that.
I mean, so the problem is that here, so now we are talking about, just so that everybody see what we are talking about. So now we were talking about this figure, I think. Let's see if this figure.
Yeah,
so Sichen was asking how to get to have this figure. So basically like this density of state, but not just that much the density of state, because the density of state you know how to do, but it's this T to G, E, G. Okay.
Yeah.
So these things, are some, like, actually some, okay, the legal field theory. What is, let's see if we can find some. So these are just like combinations of the orbital you have. No, this is taking too much time. Okay, yeah. So the way that you, like, in order to do that, you should know what is the combination that gives these things, okay? Okay, yeah. So let's say, like, you have, like, well, the d orbital, exactly, and then, like, depending on the, like, d orbital that you have, you get different, I think this is kind of the, again, like what we said yesterday, that is, yeah, okay. That is the, like, the occupancy of the electron. So basically, like, one of these is the anti-bonding orbital, and the other one is the bonding orbital, and depending on how two atoms pair, you have, like, the electron that goes either to this this T to G or this EG, and then depending on where you are, then, like, you have different occupancy of the electrons. Okay, so the way that you can calculate that, you need to come back to understand, like, what is, yeah, you see the non-bonding orbital. So how this T2G orbital is formed upon hybridization of like some d orbitals, and then you plot it. So the idea of doing that is that you probably already did it, so that you go directly on, like on the folder. So you go here, then, well, I didn't put it yet. So you open Anson 4, then this was for 3. And then Python for VASP, you go to electronic. So you go here, then electronic. Well, actually, local DOS P-bound control. And then here, you will need to select some of these D, depending on which one of these D form this bonding or antibonding E, G, T to G. But this is something that I don't know. So about that, you need to check literature, see which one of these one form this antibonding, and then you plot it. Then you select, I don't know, if the EG is given by this D, XY, and D, Z2, then you select your nickel, you add your line as, like, let's say we add it in red, and then we add in line, okay? And then you can say that this is your EG, but before you need to make sure that this EG is actually a like bonding orbital or antibonding orbital formed by the combination by these two orbitals, and that I don't know, okay? So whenever like you get to this fancy parameter like this one, exactly this T to G EG, the first thing that you need to do is like you need to check TG bond nickel, for instance, orbital, and then you will find online some, yeah, exactly which orbital are involved in TG. Yeah, you see the DXY, DXZ, and DYZ orbitals are collectively called the T2G orbital, okay? Whereas the two, okay, maybe let's open it a bit because this is too small. So now you have the answer, okay? So you should have plot, like you can plot, I mean, because exercises are for tomorrow. So you plot DXY, DXZ, DYZ, and these are the two, the T2G orbital, sorry, and then like the DZ2, DXZ square, X square, Y square are the EG orbitals, okay? Clear now? So you just go here, and let's say if you want to put the EG orbitals, then you just plot like the one with the square. And otherwise you plot the other one. Okay.
So, but I don't understand what are we gaining plotting those orbitals? Which is the
I mean, what you gain in plotting that is that in coordination chemistry, like one is the bonding orbital, the other one is the antibonding orbital.
Okay.
So depending on how like how much electronic density you have in some orbitals rather than the others, then you have your bond that is stronger or weaker.
Okay.
But again, like I never plotted myself in my life, so it's something that you never do. I mean, this is very, very, very important if you do homogeneous catalysis, if you work with complex. But when we work with heterogeneous catalysis, usually like we have a metal, we have a lot of electronic density, so there are other like models to check the bond strength rather than to see how like the two orbitals are occupied. Okay.
And do you know what does this values mean?
I mean, this value, we talked about that yesterday.
Okay.
So I can repeat. These values are, this is the magnetic moment of the nickel.
Oh,
and this is 1.21 boron magneton. Here is missing a me, I think, like the Greek me, because the unit of, well, we can actually open it. So if you go to, if you check like magnetic moment, so magnetic moment is a magnetic, and here at one point you will see a Bohr happening. Yes, unit. Alternative definition. there is not a Bohr, really? Okay, let's see. Ah, yes. Yes. Include the Bohr magneton. So this is the Bohr magneton, okay? Like the unit here is the Bohr magneton. So here in this slide, you are missing a me, okay? So this is the magnetic moment of the nickel that you get from your simulation is 1.21 Bohr magneton, and the experimental value is 1.70 Bohr magneton, and this is the bandgap. This is the bandgap. So this is the bandgap. That means the difference between this state and this state. So this is basically like the range of energy where you cannot have any states for the electrons. So where your electrons cannot be. And that is the bandgap because it means that the electron needs to move from this, that is the valence band, to the conduction band. Okay? Good. Done with your part for now, teacher?
I think, okay, it's the same thing that we have, so this is equal to the before about the T2G.
Yes. Yes.
And that's more.
Okay, good. Then Mariam, you can go ahead if you have time.
Okay, thank you.
So,
May I share the screen?
yeah.
Thank you.
So now you have all the audience, eh?
I think my screen is too small
Yeah,
for you.
try to click. So if you try to do LS in like the terminal that is in the bottom right.
This one?
Exactly. What does it happen? Try to put like LS and then enter. Yes, okay. That means that is not connected indeed. Okay, so the problem is up, you see. Let's log in. No, but I think, okay, let's try again. So close all the terminal, okay? Close all the terminal and let's start from scratch because then we also are recording this session so we can check it again. So you open a new terminal and now what you want to do is just to, let's do actually, let's do the easiest thing before. Just enter Tekla Home. So remove this line and just do like CD space Tekla Home. And let's see what you have in Tekla Home. Or you can go up in history. You should have said, okay, good. Then if you click tab, exactly, enter LS. Okay, you see that you don't have anything, okay? Because of course we didn't enable any tunnel, makes sense. Now, go back to the parent folder, so CD, like exactly, and now you do like tunnel one space, and then your exactly, you already remember. Then here you ask your password, and you put your password. Now you open a new terminal. Now, well, this is then to enter Tekla Home, but like
Okay, no need.
Perfect. Now you do tunnel 2 with your Excel. Yes. Okay, now CD space Tekla Home LS. Okay, so now it works. What was happening before is just that, you know, like this connection, like in order to work, need to have always the internet connection. So what it happened is that if for 1 second, like the internet band is a bit low, then the connection breaks. And then you need to establish it again. So to close both this terminal and to open a new terminal again to repeat the process. So what you saw before, if you remember, there was an error like broken pipe. That means that the connection is broken. So like there is no way you can come back to that. You need to start again both the process. But for instance, now if let's see that, let's just prove that it works everything. So try to enter like CD Anson 1 or well, one of the simulation that you run, I think, LS. Okay. Try to open one of them. LS. Okay, now try to do Python for VASP. So P for V space VASP run. Without A yet. P for V, exactly. And then VASP run. You can click tab. Remember, if you click tab is auto exactly and then enter. Yeah, perfect. You see?
Okay. Oh, okay. Thank you.
Yeah. And then just remember that if at one point it doesn't work, it's simply because the connection is broken. So it's not your fault. You just need to close the terminal and repeat the same process, okay?
So there is no need to open the third terminal, is it?
No, exactly. There is no need. Like the only terminal that you need to keep it open is the tunnel one. Because basically,
Okay.
let's say the tunnel is like the tunnel one is opening one door, okay? And you need to keep the door open. But then the tunnel two is just, let's say, to connect to Tecla Home. So once you connect, then the terminal is done. You know, like the tunnel two is just you connect, and then in the terminal you can do whatever you want. It's just the tunnel one that you need to keep it open, because otherwise the door will close and then you cannot enter anymore. Okay.
Okay. Thank you very much for that.
Don't worry. And then, like as you were already doing before, like in case, for instance, you want to enter Tecla, yeah, you see now that you can do whatever you want on the output. Well, very well. And then, for instance, you can close this. And now, if you do what you were doing on the left, so this SS8 exactly, now you enter a supercomputer. So now you put your password. Exactly. So you see on the left, you have the supercomputer where you run simulation, and on the right, you have both things mounted locally. So then you can play with that. Okay. Now try on the right. So on the terminal on the right, click Control C. Again. Yeah. Click it exactly. Well done. And then try LS. Okay, you see, so you still have on the right your Tecla Home mounted locally to play with, and then on the left, Tecla Home to run simulation.
By the way, if I need any change on P4 VASP, I need to do in the second terminal, yes?
You can change things in both terminals. Okay?
So no different. Okay.
So the point is that they are, let's say, it's like if you were working in a Google Drive. So both things are connected. Okay, the only difference, and probably also like the other guys here already saw that, is that in Tecla Home there is some kind of security feature, so you cannot click the delete button. So if you try the VI on the supercomputer and you try to cancel something with delete, it does not work. Yeah, so for instance, we can just try it very, very quickly, you know, try to on the left, so on the left terminal, actually do write VI space test lowercase, exactly, enter. No, it's good like that, huh? No, you can remove, exactly, perfect like that. Then try, type I, exactly, and then write whatever you want, like hello, how are you, or whatever, okay? Very good. Try, then space, add another word. Okay, good. Now try to remove hello. It worked. Usually, it should not work, but probably because, okay, then try to save it. So click S. Yeah, I think so. I think that's the point. So, no, S, and then exactly. No, put double, yeah, exactly. You need, Q is the last one, exactly. Then Q now, enter, good. Now, go up, so repeat the same command, VI space test. No, go out, because test also needs to have the underscore, because the file that we had before is with the underscore, yeah? Okay, now try to do like I, click I. Try to remove now.
I cannot remove it.
You cannot, exactly, because as Enric said, after you save, you see, like, if you do the same process on the other terminal, will work. You would be, in this one you cannot, for security reasons. So the way, for instance, if you want to remove the sentence, you need to type S. So S, exactly, and then you put 1, the number 1, and then D.
Oui?
D of Dattila.
Okay.
And then enter. Exactly.
Uh-huh.
So this you are just telling the script, look, delete sentence, line 1, okay? And now you can go
Okay.
out, so ask, and you repeat the command before.
Mm.
Remember, like ask, then the semicolon, No, you also need to put the right, so the W.
Uh-huh. To save it.
Excellent. Yes. Enter. Good. So now that works. Do you have any other
Okay.
one?
No, thank you. It was okay, you know.
Okay, good.
Yeah,
So,
each stage I'm just trying to find out more.
yeah, no, I mean, take your time, play a bit with everything, like, because it takes time, but at least the good point is that now the technical things are working. That's the most important point. Okay, good.
Thank you very much.
Thanks to you. Okay, then, question here from Enrique and Santiago, since we can already ask them. If you have something, then like.
I have two questions.
Mhm.
One is about the Duderev approach. I understood that it's as you said, an artificial correction to DFT in order to
to the energy of the electrons.
to the energy. Okay, so I was thinking, since we can also I don't know, change this value in order to find the experimental magnetic moment. It's fair to say that there are different optimal U values for, I don't know, since we have just one parameter and we want to compare with both maybe experimental magnetic moment and energy, experimental energy.
So and that's the reason why I was saying that, like, the problem is the U, in the sense that as you say, you can optimize the U given the property that you want to reproduce better. So you have for instance, like if you want to get the best magnetic moment or the best electronic properties, it will be very nice to have a very high U, because higher the U, more accurate the magnetic moment is usually. But the problem is that absorption energy get way worse if you have the U. So to calculate absorption properties, so how a CO bind on the surface, then it's better not to have the U. So that is the problematic thing, because depending on what you want to calculate, then you might need to use the U or not, and there is no optimal value in general.
Because then, as you said, changing the U, you will also change the energy. So
the point is that
there is always a trade-off.
Exactly. If you change the U, you change the energy of your system, the overall energy. Usually the differences of energies keep constant. So if you're calculating absorption energy, it should not change much, but still it changes a bit. So let's say usually like the best way to calculate absorption energy is not to have a U. If you put a U, maybe you have an offset of 0.2 electron volt. That is not crazy, but still, I mean, in a paper can make a bit different to have a 0.2 offset electron volt also. So that's the problem with the U, and that's the reason why, let's say, in the state of the art, and that's the reason also why we went through that rather fast, because you may find people that tell you, look, the U, you need the U, because otherwise without U, your system doesn't make any sense. You will find other people that tell you, look, with the U, your system doesn't make any sense, so please don't use the U. So, and there is no like solution, let's say, like I also in conferences, I've seen people not using the U, and then people complaining like, okay, but why you didn't use the U? And the other people like, yeah, because the U doesn't work. And they're like, yeah, I know that doesn't work, but still, you still need to use it. So it's like, it's not a good approach. And that's the reason actually why, and you can ask George in the group, because he has worked a lot on the oxide. That's the reason why usually people don't work much with oxide. They prefer to work with metals, because in metals you don't have the U. So in metals you are safe. The problem is that usually the oxides are also the more interesting materials, also because they are more difficult to simulate, so there are not that much simulation on that. But as you say, just to sum up, no optimal value, and you need to optimize the value given the property you want to calculate.
So is it completely artificial, or is it based on some physical, I don't know?
I think it's completely artificial. I mean, let's say the physical idea behind is that, so the problem is that is this self-interaction error.
Okay.
So the problem is that you have the self-interaction error. So let's say you are overestimating one parameter, you are overestimating the repulsion of the electron with itself, that doesn't make sense. And so you apply a kind of linear correction to the energy of this electron.
Based on this justification.
Yeah,
Okay.
based on that. But the problem is that since, let's say, the first error is an artificial error itself, then also the solution is also artificial. It's not that like the solution is to come back to a more accurate or like the analytical solution. It's just to apply a numerical correction on top of an artificial correction. So that's the
So
reason why.
the reason why we can try different EU values is because we are not able to quantify the error due to the.
Exactly, because we don't have a clear. Well, I mean, there are ways to do that, but they are really expensive. So it's still much cheaper to use the U. And if you're really curious about like the U, you can now we'll share. Just give me a second, because in the group there was Nathan that some of you didn't met. Well, Santiago met, and he worked a lot with this. And one of the last paper, it's a kind of evolution in the sense that like is okay, without here is to try to see exactly. Yes. Okay, so I just share the screen now. Yeah, so if you are curious more about this, you can check this paper. Okay, this paper is from the group. There was Nathan, I mean, and Tobias. Tobias actually gave a seminar, and the seminar was about this paper. Okay, so cerium oxide is also very painful because cerium has the F electron that is localized, so you need to use the U. But no matter which U you use, still like there are problems. So like in this paper, they started like using an alternative approach. So just forgetting like the use of U and use this many electron correlation to kind of quantify this self-interaction error. Okay, so this is a completely different parameters, parameters approach, and it's much more stable, but still, we just started. Okay, and I mean there are also not just in our group Nathan. I mean there are also other people that try to improve this U, but takes time. Okay, well, improve the use. Actually, it's not even to improve; it's just to go beyond it. Okay, then other point. Santiago.
I have a stupid question related to the last sentence. What does the car suffix in the VASP file stand for?
Car?
You know that you have out car, in car, post car. I was just curious about the car.
I have no idea.
No.
Question.
Yeah, I have no idea.
Huh?
Yeah, no, but I don't think it. I mean, you see, like.
No, this is sorry, very.
No, it's not a stupid question. I mean, it's actually
Try to find a solution.
But there is no. Yeah. You see, so the problem is that you need to imagine that all these physicists that make this stuff, they are really net. Okay, and you can check that because if you open the out card, for instance, I mean now. Okay, now it does not show that. Yeah, because I am. Okay, I will open another one. So if you open a standard, let's say calculation, so let's go for the Initio one, for instance. Like sometimes they tell you it's not even some mistakes, it's just some messages, some warning messages, but they tell you in a very artificial way. Yeah. Okay, yeah, I mean, this one is still kind of okay, the way that they are saying, but you know, like sometimes you get some warning, like, oh, I hope that you know what you're doing, or I hope that you are the master in the field, or may the force be with you, you know. So I guess that this car, maybe, you know, that they, because in all of them, like, you know, that like in parallel to this VASP, there is also another like software that some people in the group use that is open source actually, and it's called Quantum Espresso. And it's called Quantum Espresso because it was made by Italians, and espresso is for the coffee. So, I mean, actually, VASP still makes sense because it's Vienna ab initio simulation package. So, I mean, that makes some sense. But you see, so I think, I don't know, probably maybe one of the Yeah, it may also very well be that maybe the boss had a son or daughter that was playing with that toy car, and then was like, yeah, let's call it car.
Could be.
But that should be a good question. I think if any of us go to a conference where there are like the bosses of this VASP, it makes sense to ask, you know. Because,
In the book, we are now at the introduction of the fundamental theory. In that book, I think in the first chapter, there is that the Inca is the things that you should say to conduct the car.
really?
Yeah.
Okay. Okay, no, then we have the explanation. Then that's one. That's good. I mean, I
And,
suppose it was a joke, but no.
Yeah.
Good.
But there are also another concept, I think the warning, and every time that we enter
Which one do you want?
A, for example, the warning. I always have the window warning if we enter the A and equal that.
Yeah.
The government always has a warning. If this warning will affect our calculation.
No.
Okay.
I mean, the warning is just telling you that, like, this warning, for instance, is just to improve the time that your simulation will take to converge. Because, yeah, the problem is that, you know, in this answer, maybe I will quickly go over that. Yeah, we'll go over that tomorrow when we have, like, the last correction. Because, like, there are some parameters that so far we didn't use that you can use to optimize the performance of your simulation. So for instance, if you see my in-car, you see this parallelization, okay? This parallelization that you never put is simply like a way that you are parallelizing like the algorithm that VASP is doing so that the simulation will run faster on the nodes that you are calculating, okay? So for instance, I was simulating this one on the Q24, so that means that you have 24 nodes. And if you have 24 nodes, then like I use n par equal to 24 because that means that what VASP is doing is dividing all the operation over the 24 nodes, okay? And that works a bit better. But about that, I will go through that tomorrow calmly, just to give you a few tips that actually are on the wiki, so you can still also access the wiki. And I mean, this value will not change the quality of your simulation. What will change is the time that your simulation will require. So let's say if you don't put any of these like number, no problem, the simulation will run perfectly. It will just take more time. If instead you manage to optimize properly, then it's going fast. Okay.
The warning is it's not optimal.
Exactly. The warning is like, look, good simulation, you are not running it in the faster way ever. That's true. And then you can say, look, I don't mind and I like to waste time, or you can be like, no, well, I want to improve the optimization because then I can have the result faster.
Yes, I wanted to ask, first of all, in the simulations that we're running, in the first one, which is the Costco command that I have seen in the wiki. It's about one kind of calculation. My question is, when are we using that type of, well, like different solution?
Yeah, so let's just go to the description so that everybody see that. So, okay, so 0 and from 4, and then is the 1, no? The
Yes,
first one.
yes, it only appears on the first one.
And the in-car. So we are talking about
Boscon, and number 1 is just to set up that it's like a 0 or 1.
Yeah, I never use it in my life.
Okay, perfect.
So we can see. I mean, I think like there is a way, but I don't think you will really use it in your life. I mean, I just left it there because yeah, like let's see. Yeah, you see, this flag is not relevant for most model grading corrected functional. So we usually use PDE. So that means that like this parameter you put it probably Yeah, it's better. Yes, okay. The words could be usually announce a magnetic moment and magnetic energy. So I would say that you use it equal to 1 if you have some magnetic properties. Nickel makes sense. But I mean, you will see the difference just if you use LDA, so not with PD. So don't worry about that. Let's say with the system that we are using.
After that, as I saw, we are setting the MCAT on the second and well on the oxide simulations, but not on the first one. And as we talked about it in the transmission course, we can. There are some cases where we can rely on the default energy cutoff. So one of those cases, and it's more like a general question about everything that we are learning here. But one of the cases when the cell volume and positions are fixed. As I understand, it is only gonna change if you are using some commands kind like inif.
Is it? Yes.
Is it? Sorry.
Yes.
And so if you are not setting any inif, this is gonna be fixed.
Yeah.
So in theory, you don't need to change or to fix the entry.
I mean, you need because the default is not good. Like the default, so the default they are always putting. Yeah. So yeah, you see, like the default is and max on the podcast file. And now, if you go to the podcast, so if you do more
I
podcast,
think it's 270.
exactly. So the point is that this is good, but we usually take it at 450.
Okay.
Because I mean, let's say this podcast, you need to think that they were optimized, like you see the age. I mean, this is 19. So these things were optimized 20 years ago. So that means that these were optimized in a time where the computer were much slower. So they were using exactly the minimal setup to have meaningful results. Now we are lucky that the computers are faster, so we can be a bit more confident. We can put 450, and that is very important, you know, because like for instance, whenever you will write a paper about DFT, you put the energy cutoff, and if you put energy cutoff of 270, the reviewer will tell you, look, we are not anymore in 2000. Now we have good computers. Rise it a bit to 400. And as you say, if you need to do a bulk optimization, so to use this if, then you rise it to 600 electron volts instead of 450.
Okay, but here we're setting to 250.
Here we are setting to 250
because we don't need anymore.
No, because Anson they were lazy and they did this like 10 years ago, and I think it makes sense not to change it like when we do them, because then you also realize that these are bad simulations.
Okay, so after that, I saw that some of the simulations are using also EDIF, which is to set when the electronic relaxation ends. And I was looking also for the EDIF G, the one more referred to ionic relaxation. And just to summarize, the same question comes from we are. Okay, the electronic loop, it is always working. So if we want to change the default value, we will use if, I understand. But in the case of ionic relaxation, it's in the cases that we are setting that the atomic positions are free to move, right?
Exactly.
If we are not setting that, it makes no sense.
So just to summarize the good point of Henry. And I show you my own calculation, okay? So this is the income of a bulk system. Nickel, okay? You see that there is magnetism because nickel is magnetic. You see that the energy cutoff is 600. Why 600? Because I'm using EZ3. So I'm letting the cell move it. So I'm changing the volume and I need to rise the end cut from 450 to 600.
And here, sorry, you're simulating just like nickel.
This is just the bulk of nickel. I'm optimizing the bulk of the nickel. So I'm changing the lattice vector to get the lowest configuration of the bulk, okay, of nickel FCC. Basically what you did in the Anson, but with the nice setup. since it's a bulk optimization and I also want to make it a bit better, then I use additive to the power of -6 electron volt. Usually -5 or -4 is okay, but since it's the bulk, and usually the bulk are really fast to optimize because there are few atoms, I use power of -6. And then the other important parameter, I use it here, okay? That additive, so basically like the threshold for convergences of forces is set to -0.02, okay? Electron volt over Angstrom, okay? And then I am using equilibrium 2, easy 3, so I let like the volume and the cell able to relax. Then the potting, since I'm using equilibrium 2, remember, is like the first step of motion of your atoms. And then NSW is the number of like ionic steps that I let the system do. You will see in the Otsikar that here I'm finishing after 3. I'm not going to 100. But why I'm not going to 100? Because here my system already reached the electronic convergence, okay? So like for instance, if you open the Python for VASP, then you will see if you go to convergence, forces, well, I mean, you see, well, here you don't see much because it's actually very, very low from the very beginning. But the point is that it's kind of going down. I mean, yeah, like it's really, like the point is that the forces here are already very, very minimal. So that's why you don't see much. But like it's slowly going down and is going below the threshold that they put. I mean, you will see this better in the next example that I'm going to show. So if now we move to, for instance, surfaces. So let's open, for instance, nickel 100 and, well, let's make it a bit more funny. So we go with the intermediate, okay? So this system is a nickel plus an organic molecule. So, I mean, organic molecule, this is just CHCO, another, well, nothing special, okay? If you want to visualize, we can visualize it. So the system is this one. You don't see it. Here I wanted to study the coupling of CH and CO on nickel, so I put them close to get the energy of the initial step. And then if you get the forces, you see that now they are going down. I mean, well, I'll open the previous VASP run because then I have more steps. This one was already converged. So here you have more actually. So if you go to forces, yeah, then you see that now you have the forces that go down. Remember that like you always want to take the average. So this one, that is the black one, even though like now it's very small to see. Exactly. So you see that like your algorithm is trying to minimize the forces. So
is it normal to have all these oscillations within the convergence?
yeah, it's rather normal. I mean, in forces, you see, because like if you got with energy, you see that in energy is not oscillating much. Okay, and that makes sense. But with forces, yes. And why? Because of the problem that we said the other time. I mean, the forces are changing a lot. So like, and what the algorithm does is simply to follow the gradient, okay? But what does it mean to follow the gradient? It means that, for instance, yeah, let's take it here, okay? Like you are here in this point, and then you just say, like, you have the gradient in this direction, but why? Because maybe, like here, there is the minimum, let's say, there is one of the minimums. So you go a bit in this direction, and then you are here, but then here you are in a metastable state. And actually here you are in a state where there are a lot of forces. So you go up, because, you know, like at this point, the next step is like, no, shit, I don't want to stay here. I mean, this is metastable, like, I don't like to be here. And then you go down a lot. Because in this way, you get again in the direction of the, let's say, the real gradient that go in the direction of the minima. So you go down, and then you again peak. And that happened because, well, this is intrinsically in the algorithm that we are using. Because if you remember, the algorithm like goes in a direction, stop, calculate the gradient, then follow the new gradient. And so that's the problem. Why? Because every time the new gradient may have a slightly different like position than the previous one. Okay, the important point is that at one point you reach a state where even if you're peaking still, like the average forces are still low enough. Okay, and the way that you get to know that you're reaching convergence is when, even if you don't get the threshold that you set, if at one point this profile gets flat, means that you are close to the minimum. Maybe you are not exactly in the minimum, but you are close to the minimum. And why you can also assume that? Because if you take the energy, for instance, you see that there is a lot of difference between this value and this value, okay? Because this is 44, this is 86, so this is 0.4 electron volt. But then if we go close to the last 50 step, so if we do a zoom here, so the difference between this value and this value is 0.004 electron volt. Remember the DFT has an intrinsic uncertainty between 0.1 electron volt. So, you know, like if you give this value with DFT or this value with DFT is equal. I mean, there is no difference. Even though like this one is slightly more negative, there is no difference because this is within the intrinsic uncertainty of DFT. So that's why at one point you can get this energy and say, okay, look, this is a good estimation of the energy of the system. Because again, like it's within what we can calculate with DFT, okay? And then just to see which were the input for this surface. So here I have, again, spin equal to 2. I'm using PBE, so GGA equal to PBE. Here, E charge equal to 2 because I'm starting from scratch. So I'm taking like the charge density from the overlap of the atomic pseudo potentials. And then also the E start is starting from 0 and not reading any wave car. Energy cutoff, you see that is lower to 450 because here I'm not changing anymore any cell. So 450 is good enough. Energy difference, you see that I lower it to power of -5. So that means that the electronic cycle will stop when the difference between the n step and the step n+1 is, well, 0.00005 electron volt, okay? So we are talking about 0.05 milli electron volt. So you see that, I mean, it's a threshold that is really strong already. And then is mirror 0, that is the one that you're using the Gaussian smearing, the same as before, sigma 0.03. You see that many of these parameters are the same with the bulk because you don't change them, okay? Like, because they are always the same. And then this Ibrion 2 as before. Now I put N3 because I want to save like the two like position from before, but I mean that will not make that much change. And then you see that at the now is, I rise it a bit, so now is minus, well actually also in the bulk was minus 0.03, so there is not much difference, but still like this threshold for the forces is good enough, okay? So, and this, like this one and the previous one is basically the inker that I've used for mainly all my systems, more or less, okay?
Sorry,
Yeah.
question because for my read in the VASP, it tells us that the EDFFG should be 10 times more than the EDFF, etc.
10 times more.
So if you, and so if you set the EDIFF equal to 1 or minus, well, okay, 0.00001.
Let's go to see the text together. Okay. No, this is telling you that the default of add-if is add-if multiplied by 10. Okay, so that means that is actually add-if should be, is 1 order of magnitude higher than add-if. But pay attention because this works if you have it positive, because if add-if is positive, then the threshold also for the ionic steps is in energy. But we don't want the threshold in energy. We want the threshold to be in forces. And so we put it negative, because you see that when edit is negative, the relaxation is stopped when the norms of all the forces are smaller than this value. This is usually a more convenient setting, so never put edit positive, because you don't want to converge by energy, you want to converge by forces.
So normally the diff and the value that will be set will be minus 0.03.
Exactly. Exactly, and that's all. And then you see that we have a bunch of other things, the parallelization. You will need also to include van der Waals that you never include before. And this is just to apply a correction. And this you apply only if you are calculating absorption energies, absorption properties. Because I mean, in a bulk, you don't include van der Waals because there is no van der Waals. Apart that, if you are working with graphene, for instance, you know, you can have some like van der Waals interaction between the layers, but in a standard like bulk system, no problem.
And how to type this value? I mean,
About this value, like you do it through a script, and you will get the script when you start simulating with that.
okay, because we could not know if it just absorption is van der Waals or no. So
Yeah, absorption is always van der Waals.
maybe not if they have absorption much stronger than van der Waals.
I know, no. Okay, I'm not explaining myself properly. So these values are not to distinguish if it's an interaction with van der Waals or not. This is to apply van der Waals correction in any system. So this you need to apply for any system where you are absorbing something, because this is just an overall correction. If then is chemisol and van der Waals interaction are not that relevant, it doesn't matter, but still it's better to have them in the system. Okay? Because otherwise you will need to motivate. You will need to tell the reviewer, look, I didn't apply van der Waals because I know that this atom is absorbing strongly, so there are not enough van der Waals interaction. No, it's much better just to apply them, and then you can say, look, and then after that you realize that they are not that important, but still, like, it's always better to have a correction that is negligible rather than to avoid the correction, because you cannot decide before whether the correction is relevant or not. Okay, any more points?
Yes, and the last one is about the. I think that's in the 4.3 Inca on the 4.3. I don't remember, but no, maybe in both. Those amix magnetic, the mix.
Yeah.
I don't understand exactly what why we are using those kind of approximations.
Yeah, I mean, so all this value you usually don't touch it. Okay, that was 4.3. You usually don't touch it. Neither you employ them much. Let's say, yeah, we are talking about these parameters. Okay. So these parameters are usually, the default values are good enough. So usually you never include them.
Okay.
In my case, you have seen that before, that here, for instance, actually here, yeah, here I don't have, you see.
No, I have not seen them.
Yeah. And that's the reason, because you touch these and you include these only if you have problem with the electronic convergence or the magnetic convergence of your system. So if you are working with very, very exotic like system, but again, like, don't worry too much about that, because remember that you will get the Inca from somebody, the first Inca you use in a system. It's not that you need to make the Inca from scratch yourself. You will get a Inca from somebody that should work. And then if that Inca does not work, then somebody will tell you, look, that doesn't work, you may need to add this tag, and then you add, and you check the wiki. Yeah. But by scratch is something that you don't need to include, and you just include them to speed electronic and magnetic conversion. But the problem is that there is no a rule of thumb. I mean, there you just start playing with them, and then you keep doing tests, and then whenever you get to one value that works, then you are very happy. But it's a very, very time-consuming process, because there is no solution. It's not like the U that at least, you know, okay, I improve the U and then I do a benchmark. No, there is like, okay, and also because you see, like, it's not just a parameter. I mean, these are like 4 parameters, and there are actually much more than 4. So you change one, but then you need to keep constant the second. I mean, like, as long as you don't need to touch them, don't do that.
Okay, okay, so for me, that's all.
Any more point in general? Mariam, do you want to add something? Okay. Yeah. No, take your
I
time.
remember, for which element is typically needed the spin polarized calculation?
Magnetic. So all the magnetic,
the
so
iron,
nickel, yeah, iron and cobalt, manganese. So like, you know, it took me a while to understand when, because, you know, I was always checking like Wikipedia, and I was always like, okay, let's see if it's magnetic. But the problem is that almost all the metals are poorly magnetic. It's also copper is poorly magnetic, but then of course, like, you don't see it and you don't need to apply the spin for copper. So the U is just depending on the number of unpaired electrons that they have. So like in the case of nickel, in the case of, well, now in my case, neodymium, like, they are magnetic because it's really clear that they have an unpaired electron. Well, or even more. And so whenever you have unpaired electrons, then you have magnetism. So for instance, like oxygen, if you remember, like the P electronic configuration has paired electron here, and then they have 2 unpaired electrons. So if you have 2 unpaired electrons, then you have magnetism for sure. So you just need to check the number of unpaired electrons, but in general, the rule of thumb for the transition metal, as we say, like nickel, cobalt, manganese, and iron, and that's okay, because then palladium, platinum, silver, gold, copper, tin. I mean, for instance, tin is also partially magnetic. So let's say, again, like, how do you do that? Like, let's say, if you want internally to work with VASP, when you optimize the bulk, usually I always try with spin or without spin, and I see if there is a difference in energy. If I see that there is a relevant magnetic moment in the system, then I consider including the spin. If I see that there is no difference, then either I don't use the spin or you put the spin polarization. I mean, like, in principle, to add spin polarized calculation is not bad, because if, like, there is no magnetism, it's not that your simulation will be wrong. The only problem is that it's a bit more time consuming. So that's the reason why, if you can avoid that, it's better, because you will save time. Okay? Good. Yeah, I had a very quick question for the 4 of you. Because I was wondering just yesterday whether, like, you think it makes sense to have, like, tomorrow, since it's just three exercise. So I mean, tomorrow actually is correction, but like, it's just to make sure that all of you manage to solve it. So like, I don't think we'll take a lot of time, because there are not even questions. So I was wondering if you are interested in having like 30 minutes introduction for dummies about Blender. That is this visualization tool that I mentioned to some of you.
Yes,
Okay.
I haven't heard about this, but yes.
Yeah. So okay. So also to explain you, Mariam, and that is not problematic, because this is a standard software that you can download on Windows, and it doesn't require any permission. So like, this is like downloading, I don't know, Word. So like, that for sure will not be a problem. But yeah, just to tell you what it is, because then if you think it makes sense, then we can then we can directly work on that, like, tomorrow for 30 minutes. So Blender is a visualization tool, okay? And now I just show you a very quick example. But before, I want to clean a bit the things. So I have a lot of things. So this one, this one, this one. Okay. And then like this. Okay, so Blender is a visualization tool that usually, okay, you use for doing images, okay? And as I said, like, tomorrow, if we do it together, it will be for dummies, because I use it for dummies. but you can use for doing a lot of things because it's a 3D visualization tool. So you can actually use it to do a lot of things. It's very nice. And I think that if we go through that tomorrow, then it's good if all of you bring the computer, because then we can work on that in parallel together. We make sure that everything works. But just to show you what you can do, okay? So for instance, you can import like the position. So this is a concar file, okay? This is a structure from any of your VASP simulation. You import it. And then here you have your system, okay? And then you can, let's say, you can move your camera, that is this, where you want. Okay, so maybe, let's say, if I want to go to do something that is the top view, I can put it 0, 0, and then I put it, I don't know, like 50, and then 0. Okay, I will. Okay, yeah, it's actually almost there, but now, yeah, okay, now it's just. So let's say you play with the camera, you play with the light. Tomorrow we can see that. But the nice point is that then, for instance, you can generate nice picture, okay? Because then you can change the colors here, but I'm not going to do that. But the nice point is that then, if you click F12, you can render. Yeah, now we'll take a bit more time because I also have Zoom open. No, but also because this is, yeah, this is the standard rendering. It is taking too much time. So we're just changing. I mean, now it's a really bad image, but it's just for letting you know. Like then, like here you see also that the light is rather bad because it's just on here, but you can also adapt the light. And then, for instance, you go to image, you save at a PNG, now it's entitled. And then, let's say from Blender, you can print, you can get the image. So now here, this is just the image that we just printed, okay? And you can change the color, you can change the size of the boss, you can change the light. And it can be nice because if you are doing any kind of heterogeneous catalysis, it's nicer to get like this nice molecule on top, and then you can also do videos if you want. So are you interested?
Yes.
Should we do? Okay. Then as soon as we finish this, I'll send you an email with the things that you need to download for the one that doesn't have Blender. Actually, that will be the only situation where it will be easier for Mariam, because for Windows it's very easy, because for Windows it's just, an executable, so you click. With Linux it's not more difficult, because it's not more difficult, but it's more challenging because in Linux you need to do the things yourself. I don't think, probably you can also do it from the terminal directly, but I never did it myself. I just like moved the executable in a position. So I'll send you like the information, okay?
Okay.
And then tomorrow, let's say we dedicate 15-20 minutes to go over the exercises if there are any problem, and then the other 30 minutes brief introduction. So remember to have the computer with you, and also Mariam, like in your case will be easy because you just need to keep the windows open, okay? And then I will, and then let's say I will already give you the structures that we will work with. So you don't need to do anything. Basically, like I will send an email when I said, if you look, download this package, like download Blender, and then also download these 3 surfaces that are the one that we will work. Okay? Good. Then I think, that we are done. So I stop sharing.
You more like me?
Huh?
More like me.
Then tomorrow I will show you how to change the light and everything. The point is that you see, like, it's very easy to generate a graph with Blender. Then, like, better you want to get the picture, more time you need. So, but that is up to you. It is something that if you know the basic or which are the parameters that you need to touch, then you can do, and you can do really beautiful things. Like, and it's not my case, but I was talking to Santiago, yeah, like we had a colleague in the group admin that could really do, because then you can also do things in 3D. So you can actually do, well, tomorrow we'll also send you like, because he has 4 tutorials on YouTube where he's doing nice things. Because you can also do like batteries in Blender, you can do whatever you like. But in our case, we will just go for Blender for that, because I think it's the introduction, and then if you like to spend hours on that, go ahead. Good. So I think that if there are no questions, then we can close the session. Good.
Thank you very much.
Ciao.
Ciao.
Bye, Maria. See you tomorrow.